Okay, I want to start talking about so-called Bohr model. So a short note. So Bohr developed his theory prior to de Broglie. So he didn't know about these matter waves, he didn't know about this relation, but it's easier to derive his result using de Broglie. If I have time, maybe today or maybe next time, I'm also going to show you how Bohr came up with the quantization. But today, we use de Broglie relation because it's much faster to get the result. So let's repeat the argument. The central force should be equal to electrical force, right? The Coulomb force, and mv squared over r should be equal to, let me call this k e squared over r squared. And from here you can get mv is equal to, right? Just multiply with m, delete this, delete that, and if you get this, mv is going to be root k e squared m over r, which is momentum. Now use de Broglie. Wavelength is equal to h over p, which is equal to h over mv. Why mv? Why should I use like relativistic momentum? Relativistic. Any suggestions?
In the case for electrons, we should use relativistic.
And now, how should I decide? Look, right now I seem to have a classical momentum. How should I what is the principle? Given a Yes, but I give you a problem, right? A single atom, and I know energy scales, right? From our discussions before, we know the energy scale that necessitates the use of relativistic kinematics. What is the energy scale? Yeah, this is like 0.52 MeV, right? This is a gigantic scale. But for the atomic scale, what is the energy scale in atomic physics? From high school, there is only one number everybody remembers. What is it? Anybody? In electron volts is a little better because in atoms. What is the only energy in electron volts? I think everybody. 13.6, right? So in atomic physics, we have 13.6 eV. This is much, much smaller than this, so we can forget about relativity. Okay? In atomic physics, we can use classical momentum. So the answer is use of classical momentum. Non-relativistic momentum is sufficient. And now from here I found, okay, I have h over mv and I have an expression for mv. I can plug in and find lambda is equal to h squared r divided by k e squared m. Again, like experimentally, we know, I think this experiment has been known like I think basically forever. Experimentally, ionization energy of hydrogen atom is minus 13.6 eV. And if you equate this to this energy we found 1/2 k E squared over R. Right? K is a constant of nature. We know E is electron charge. This is energy. You can solve this equation for R. Right? That's the only unknown here. And you are going to find R is equal to 5.3 times 10 to minus 11 meters. So that's the radius of the electron orbit, which is known as Bohr radius. We'll see later. And from here, you can plug it in here, right? H is Planck's constant. K is like this 1 over 4 pi epsilon naught. We know E is known. Mass of electron is known. If you put this R to here, the lambda is going to be order of 33 times 10 to the minus 11 meters. So that's the kind of wavelengths we are working with in this problem. And here is Bohr. So Bohr considered fitting a wave around the orbit. Let me explain. So if you remember, we had like a particle in a box. We had a geometry like this. And in this case, we said like the ends are fixed. So the allowed wavelengths are things like this, right? But now we have like an orbit. So we have to think about deforming this shape to an orbit. Like maybe I can do it in two stages for you to see what I'm doing. Like maybe in the first stage, I can curve it a little bit like this. And the wave is going to do the same thing, right? So let me push this a little bit. And in the second stage, I think you can kind of see where I am going. In the second stage, I can complete the circle, something like that. And this is the orbit. And the wave I'm going to fit is like something like that, right? If that confuses you, you can just break it from here and then open it up. It's going to bring you back to this picture. So this is what I call ground state. So I can have like more nodes in the orbit, and I can have like so-called excited states. Then the basic principle to determine these excited states is like this. The length of the orbit is 2 pi r should be equal to wavelength times an integer, right? This is exactly what we did for a particle in a box, right? We quantized the radiation with the same principle, and n is equal to 1, 2, 3, dot, dot, dot. And the first one, maybe I can just give you a couple of examples. So the ground state I want to draw again. So it's half outside. Okay, this is a little bit sloppy. So half outside, half inside. Okay, this should be a circle. Maybe it's harder to draw in this tablet. So the second one is, I don't know, I have to do 1, 2 of these, something like that. So the third one is something like that, right? So this is n is equal to 1, what I call ground state. So this is n is equal to 2, first excited state. And this is n is equal to 3, second excited state. Good. Yes?
Do we take R as constant?
No, each R, right? Like R is going to be like also like, there are different ways, right? You have like a radius, and in that radius you are supposed to fit the wavelength, right? And you can, yeah, like this, there is like a smallest unit of wavelength, right? and you are going to fit multiples of this wavelength. And every time you fit one more wavelength, radius is going to increase. Okay. So let's write an equation for this. So 2 pi r is my circumference, is going to be equal to the integer times wavelength. But for wavelength, we had like this expression. Let me copy and paste this. So I think this answers your question a little better, right? On the right hand side, I have r. On the left hand side, I have r. On the right hand side, once I write what lambda is, it's also r. So solving this equation determines both r and wavelength, right? So the two unknowns. The answer to your question, they are both unknown, but I have to choose both of them in such a way that this quantization condition is satisfied. Now you can solve this equation, right? Let me get rid of this intermediate guy, and so this is, let me take the square, this is n squared, this is 4 pi squared r squared, and this r is going to cancel this r, and I am trying to find r, so then r is going to be equal to, maybe I can put like an index to r now, because each n is going to give rise to a different orbit, and r is, okay, if you cancel everything, let me write it, n squared h squared over k is 1 over 4 pi epsilon naught, this is e squared, this is m, and I also need to have 4 pi squared. So this 4 is going to cancel this 4, this pi is going to cancel one of the pi's, and I'll take epsilon naught to here, and I think that's the final form. Okay, this is pi. Good. H squared epsilon naught e squared m times pi. Again, define Bohr radius. Okay, Bohr radius is defined for n is equal to 1. Then a naught is equal to this h squared epsilon naught divided by e squared m pi, and it happens to be equal to 5.292 times 10 to minus 11 meters. And if you remember, energy was equal to minus a half times, or half of the Coulomb energy is total energy. I think we derived that in the beginning. So minus a half e squared over 4 pi epsilon naught r. Now I can substitute this r to whatever I found, rn. Is that clear? I already had this r. Now I'm just saying that only specific r's are allowed, and these specific r's are going to give me specific energies that are allowed. And this is going to be minus a half e squared over 4 pi epsilon, and then this is n squared h squared epsilon naught divided by e squared m pi. So I'll erase this and I'll write this e to the 4. This is m and this is gone. This pi is going to cancel this. This 2 will give me 8. I think this is epsilon squared, and it is going to be equal to minus 13.6 eV over n squared. How do I know that? I know that because if you multiply all these numbers, e to the 4, m 8, epsilon squared, h squared, that gives you 13.6, and its unit is going to be eV. Now we can talk about origin of spectra. So let's consider origin of spectra. So basically, we have the nucleus with positive charge, and around nucleus we are thinking about these quantized orbits. And you can put an electron to in one of these orbits, but you can also put them in like a higher orbit, right? And anytime electron wants to come down to a lower orbit, you can do that, but there is like an excess of energy which should give rise to radiation of energy. And what we need to do is, okay, electron jumps from one Bohr orbit to another, and we have to account the energy. E initial minus E final should be equal to, right, this energy should go to somewhere, and this, in our case, which is the radiation, goes to light. And from here we know this from Planck, because this is the photon energy, and here we know this from Bohr model. And E initial is equal to, let me call this E1 is equal to 13.6 eV. Some people want to put a minus sign. Don't confuse yourself. Whichever is more comfortable for you, do it that way. Then it's going to be E initial is E1 over N initial squared, and E final is going to be equal to minus E1 over N final squared. And from this accounting, E initial minus E final is going to be E1, 1 over N final squared minus 1 over N initial squared is going to be equal to H nu. But C is equal to lambda times nu, then nu is equal to C over lambda. Put this back here, C over lambda. Then we have 1 over lambda is equal to E1 divided by HC, 1 over N final squared minus 1 over N initial squared. Yes, I think so. Oh, I think the other way. I think I messed up like a minus sign. I think in my notes this is initial, this is final. You mean like this? Right? Okay, thank you. I appreciate it. And here, for example, Lyman series can be obtained for N final is equal to 1. You are going to lowest orbit, and you can obtain Balmer series for N final is equal to 2, and so on. You can obtain all these series by just choosing N final, and initial is going to be 1, 1 higher, 2 higher, 3 higher, and so on. Maybe I can draw this picture and then explain what I mean. So this is N is equal to 1. This is N is equal to 2. Maybe. So they are not equally spaced. Obviously, 1 over N squared for integer n's is not equally spaced, but for demonstration purposes, I'm going to draw them like this. And so this is N is equal to 1, this is N is equal to 2, N is equal to 3, N is equal to 4, and maybe ... There's also an N is equal to infinity. So this is N is equal to infinity. Here is the Lyman series. So this is the first one, this is the second one, this is the third one, and this is the last one, the terminating wavelength. So the second Balmer is this. So there's like this one, dot dot dot, and terminating one like this. And there's Paschen series. So there's this one, dot dot dot, and this is the terminating one, dot dot dot, and so on, right? So this is, I think this is Lehman. This is Balmer, and this is Paschen, and so on. Good. Any questions? So basically, Bohr model explains two things. First, in the Bohr model, electron does not radiate. It is in like, okay, first, electron is in stable Bohr orbits. So atom itself is like stable. And two, transition from one level to another gives rise to atomic spectra. Good?
How do we know electron is stuck in an orbit?
Like at this moment, no, we don't know, right? At this moment, Bohr only gave like a very compelling argument so far. Right now, we still don't have 100% confidence. But it seems like electron doesn't radiate, right? Empirically, we know it doesn't radiate. And Bohr said, okay, these are like stable orbits. And I am thinking like a wave, like a so-called stationary state. Right? Stationary means it doesn't radiate. But why is it stationary? Why is it like this? We still don't know. But at the moment, like because the agreement between all of these series, like Lehman series, Balmer series, and the Bohr result cannot be accidental, right? There has to be a connection, and the connection seems to be very strong at this moment. I need to talk about nuclear mass. So we assumed so far, we assumed a fixed positive charge. So is this a reasonable assumption? Should we like update anything about this? Anybody want to have any suggestions?
After that experiment,
Right.
they understood that there is this central nucleus, right?
Uh-huh.
So,
But like in real life, atom itself moves, right? Right? Nobody is fixing an atom in the center of the coordinate system. And what is the argument for us to assume that the nucleus is fixed and electron is orbiting around? Yes.
Mass difference is too much.
Exactly, right? So M proton is about 1,000 times larger than M electron. And in that case, we can, so I think some people call it like so-called Born-Oppenheimer approximation, in which you take the ions to be fixed. And the argument for this is like, actually, we can transform to center of mass and relative coordinates. There's like a little bit detail, but you may or may not know this, but you can transform the two-body problem to one-body problem, right? And you are going to have like a center of mass coordinate and the relative coordinate. Center of mass coordinate is going to be free, and you are going to throw it out because it's irrelevant. And you are going to write all of these things in terms of relative coordinate. In that case, all you need to do is replace mass with, okay, this is reduced mass, which is, okay, let me call this m prime is equal to mass of electron times mass of proton divided by mass of electron plus mass of proton, and this is going to be approximately m electron if m proton is much larger than m electron. And you can, for example, calculate the correction, and let me call this En prime, is going to be minus, initially we had m e to the 4 divided by 8 epsilon naught squared h squared 1 over n squared, and for n prime you are just going to put this m prime here, and the difference is order of m prime over m electron. I think it's like the difference is going to be m proton divided by m proton plus m electron, and this is 0.99945. Right? There's like a tiny difference, which is like reasonable to neglect. However, there are other problems. For example, you can consider maybe exercise. Consider positronium, which is like a very like common problem people may ask you, not only me but like other like physics exams, they keep bringing this problem. This is like a bound state of electron and positron. Positron is exactly like electron but positive charge, so their mass is equal, and we can also consider like a bound state of these two things like a toy atom if you want. And the question is what is the ionization energy, right? So this is one exercise we can think about it. So another exercise is, I think I calculated this in the notes, you can look at that. Another exercise is like consider muon rather than electron. And what is the difference between muon and electron? Does anybody remember? Muon has like a very short lifetime. Other than that,
It turns
what's that?
to electrons after some time.
It decays to like radiation at some point, but within it is lifetime. Suppose within its lifetime, we are going to put this in the orbit of a proton, and we are going to replace electron with a muon. What is the major difference? Mass, right? It is like, in this case, m muon is about, I think, I don't remember, 200 times m electron, something like that. So this is also an important effect. You can also consider that. How much the ionization energy differ in the case of a muon hydrogen rather than electron hydrogen. And there's like a full line of problems that can be solved by simply replacing the mass in your result. So, okay, I will give you like a very short discussion and I will finish it there. Like, there are like two mechanisms of atomic excitations. Let's consider these and then finish it there. Atomic excitations. So we have two main mechanisms. So first, two atoms, we can collide two atoms and then see how the atomic structure changes. Two atoms collide. So it's something like that. There's like a central nucleus, and I have like a filled orbit. Let me write it like this. And I have an empty orbit. And I take one of these guys, and bump it into another one, right? So they collide, and after the collision, for example, due to like the kinetic energy, you excite one of these electrons to here, maybe both if you have enough kinetic energy. Like this is going to take place in like a gas chamber. There will be many atoms experiencing many different collisions. Some of them are going to have this, some of them are going to have different things. But like a later time, like later, so this guy is not going to like being in that state, right? And it wants to like lower its energy by going here. And if you do that, it's going to give you electromagnetic radiation. This is like a photon. And this gives rise to, so this gives rise to emission spectrum. Okay, so basically you have a gas and you are just looking at what comes out of gas, and from that you are going to have like, I don't know, some spectral form. Like you have like some spectral domain and there are like some lines. And the second main mechanism is you can send radiation, right? So you have exactly the same atom. So initially this electron is like here, but I'm going to send all kind of radiations, like with like maybe a radiation with the black body spectrum, and the right spectrum, the right photon is going to hit this guy, and it's going to promote to here, right? And then when you put your detector here, you are going to see that the energies corresponding to this transition are going to be missing from this incoming radiation. And this is what we call absorption spectrum. So in this case, you have exactly the same like spectral domain, but your spectral domain is like, okay, this is full, okay, I don't know, right? All kind of like spectrum is here, but there's like a place where something is missing, like this. There's another place, something is missing here, something like that. For example, this is how we determine the composition of stars, right? From the inner structure of stars, all kind of radiation is coming out, but in the atmosphere of the star, there's like a certain composition which absorbs certain light, whereas lets other light to go through. By just analyzing what comes to us and what doesn't come to us, we can tell the composition of the stars, which is like very common in radio astronomy. Okay, this is the absorption spectrum. Maybe I can finish it here and continue next time with how Bohr derived his result. Any questions or comments? All right, thank you.